I'm Gamechangers from MIT. On behalf of the organizing committee, which consists of my colleagues Asegun Henry, John Linhart, and Evelyn Wang, we welcome you to the launching of the MIT InnoTherm colloquium. So this international colloquium series on thermal innovations is sponsored by the MIT Department of Mechanical Engineering. And then we launched this series in this special time in history. With COVID-19, we face a really urgent humanity challenge. And many of our colleagues working hard fighting the pandemic. We are grateful to your work. This crisis is also really a hint to what lies ahead of another even bigger, and in fact, the existential threat to humanity, the global warming. Heat has everything to do with global warming, from the physical origin of the Earth's temperature rise to the fact that the accelerated temperature rise is mostly due to the use of fossil fuels, the refrigerants. But at the same time, we know humanity needs thermal energy, from cooking to air conditioning to industrial processing. So the rising temperature of the Earth also create other challenges in food and water, and many of the solutions will rely on heat and mass transfer. So thermal technology really had historically revolutionized the humanity in technology, in energy, but also created problems. We need to innovate in thermal technologies. And that's why we thinking particularly at this time, many of us are locked down, working from home, and we cancel trips to conference. We have less opportunity to exchange ideas. But it's important for us at this moment to work together to address the urgent need of humanity. And this is the reason we launched this international colloquium. And then we need to go across the boundaries of a discipline, and we need to cross the boundaries of the country. I'm very happy to report that this idea had garnered many enthusiastic support from the first email I sent 2 weeks ago to now the launching of today's event. I'm very grateful to many of our co-organizers, to our staff members, students, postdocs. But I'm particularly grateful to today's inaugural speaker, Professor Arun Majumdar, and panelists Asegun Henry and Ravi Prasher, and the moderator, Chris James. I'll leave Chris to introduce today's speaker. But I want to show my slides, a few slides here. And share the screen. So as we learn to use the technology, and so this is of course the today's event. As I mentioned, Chris will introduce more on Arun. But I want to remind that what we're planning now is at least the next few weeks, every Wednesday. And here are the next 3 talks we have from, next week we have a talk on using the cold universe as a sustainable energy source by Professor Rongwei Yang. And the week after, we actually have Professor Bob Laughlin, who is a Nobel laureate from Stanford, talk about thermal storage together with a panelist from Professor Dr. Datas and also Henry. And on May 15, we have a debate on HVAC system. So we want to have this event to be on a weekly basis, and this is not the right slide. And so that's the, so please sign up, and we plan to use the same Zoom link and same time until any change. So if there's change, it's important that you are on the list so we can reach out to you. Or you can log into our website at innotherm.mit.edu. So with that, I'm going to introduce today's moderator, Professor Chris James, who is also currently Vice Chair for Berkeley's Department of Mechanical Engineering. He is a recipient of the NSO Career Award, the DARPA Young Investigator Award. His research is in the fundamental nanoscale heat conduction, thermal measurement using electron microscopy and other methods, and thermal switches and diodes. So Chris, you can take it from here.
All right, thanks very much. I'll take over the screen share then. Screen one. And bring this over and slide that. As Gong said, we're all figuring out the technology here. All right, so it's a real pleasure today for me to be moderating this inaugural session, and we have three real luminaries of this field of energy as it relates to thermo. As many of you know, they have very rich and diverse experience spanning all the domains: academia, industry, companies large and small, the national labs with their experiences. I'd like to briefly introduce all three, and then I'll lay out the agenda for today, and we'll get started. Our keynote speaker is Professor Majumdar from Stanford University, where he's also co-director of the Precourt Institute. He was the founding director of ARPA-E. He's had extensive experience elsewhere in DOE, in industry at Google, previously at UC Berkeley. He's a member of NAE, and as of this week, we're delighted to share he's also a member of the NAS, the National Academy of Sciences. And you can see his research interest quite diverse, from nanoscale imaging up to electrochemistry and thermochemical reactions at very large scale. We have two panelists. We're also very excited about their contributions today. Ravi Prasher is an associate lab director at the Lawrence Berkeley National Lab, and he's also an adjunct professor at Berkeley. He also has extensive industry experience, both at Intel and in a startup based on the thermal sciences, Şteel. He's been a program director at DARPA with these two different thermal programs you can see here, so he really knows all sides of the story as a proposer and as a manager. And his research areas span also from nano up to the macro scale energy systems as well. And our third panelist is Professor Asegun Henry at MIT, formerly at Georgia Tech. He's had three very challenging distinguished fellowships, first at ARPA-E and also the Ford Foundation at Northwestern, and also in Oak Ridge National Lab. And you can see his research interests go down to the atomistic molecular dynamics and up to extensive, more recent work on high temperature energy systems. And we're really just delighted to have all three of these outstanding folks here today for this opening of the entire colloquium series. This is the time when we'd all be kind of applauding. Please help me welcome our speakers, but we don't have that option in this current technology context. Let me tell you how things are going to flow today. We will have first Professor Majumdar's presentation for around 30 minutes. As you will see, the organizers are very interested in your feedback, both on today's session and on this colloquium series overall. So we're going to have three polls. They're all single question polls. We'll do the first right after Professor Majumdar's talk. Then we'll transition to the panel phase with all three of our panelists. And at the very end, as we wrap up, we'll have two more snap polls to get high-level feedback. As many of you have noticed already, we've disabled the chat feature for those of you as attendees, and instead you can see at the bottom of my screen highlighting here, we're going to have these two features. So the sole mechanism for the attendees to communicate with us is through the Q&A channel. This may be new for many of you. Your questions are not visible to the rest of the participants, only to us hosts and organizers. We're anticipating many questions, so we'll kind of filter those, and it'll be part of my task as moderator with 4 helpers, in fact, 4 student helpers filtering everything to recognize those and pass them on to the panelists. Please note that this colloquium is being recorded. We're already being recorded right now, and the intention is to clean it up and then post it to YouTube for kind of public viewing and broader impact. We anticipate capturing and posting the many questions that the panelists didn't have time to address today, but to put them out there for broader conversation among the community. And as you post your questions, We're very happy for you to indicate your name, and our default is that I will read off your name if I share a question. But if for any reason you prefer not to, you can just post anonymously, or you can make a point of stating when you send the question, I prefer not to share my name broadly, and we'll try to honor that as well. Okay. So that's the protocol for today. And without further ado, I'm going to hand it back over to our keynote speaker, Professor Majumdar.
Can I share my slides from here? Okay, good. Just one second. We're still learning the technology. Just one second. Great. Can you guys see this?
Yes, we can.
Great. So first of all, let me start by thanking Gong Chen, Asegun Henry, John Leonard, Evelyn Wang, and all the students at MIT for creating this forum. We are living in some unprecedented times, and we're all trying to figure out what the future ought to be. And we should be very thankful of all the medical people who are fighting, who are the soldiers in this World War III, fighting on our behalf. But it is also a moment that we should take this opportunity to sort of define what the future could be. And one of the things about the future is that I don't think conferences are going to be exactly what it used to be. I think they'll be hybrid in the future. But, we thought that this would be a good way to start. And the topic that we decided to talk about, and I want to thank Asegun Henry and Ravi Prasher. The history is that we started giving a briefing to Bill Gates about a few years back, and we have distilled that into a paper that is going to be published soon. We thought we'll talk about that and we'll have a panel discussion. So let me launch into this. The outline of the talk is these are the 5 grand technical challenges that we think are very important: thermal energy storage, industrial processes, low global warming potential refrigerants, long distance heat transmission, variable conductance buildings, and building in generals. This is going to be a technical discussion. This is not about the innovations in energy policy, finance, business models, which are critical for impact, but that's not the subject of this talk. Having said that, I'll end with what I think how we should be thinking about the future, both technically and non-technically, given the situation that we find ourselves in right now. And we could talk about that as well. So let me first give the context of this as to why we are looking at this. The first thing to start off with is population. As you can see, this is the history of the world population and what we have seen over the last few hundred years, which is a blip in the human history, is a massive rise in population. It's an exponential growth. And it is expected that by the end of this century, we'll be about 11 billion people around the world. But that is one exponential growth. The second amazing exponential growth has been that of the global per capita GDP. It is not the perfect measure of human development, but it is a measure of our, at least, a prosperity. And that has grown exponentially as well. And this is the per capita, not the total. The per capita GDP has gone up. And the question is, how did this all happen? And at the root of this is the use of energy. Without the energy, without the electricity that we have that we are currently using, or the oil and gas that we have for transportation, we would not have this modern economy that we have now, that we are trying to preserve at this point. And so energy is absolutely essential for economic growth and the quality of human life that we have developed, which has transformed over the last 200 years or so. People in 200 years back could not have imagined the world we're living in today. And that energy so far in the history has been from fossil energy. And that today provides 80% of the primary energy in the world, roughly 80%. Renewables are a very small fraction right now. We have nuclear, hydroelectric as well, but it's mostly coal, oil, and gas. Now, the use of energy, of course, has led to this economic growth and a quality of life, but it has had other consequences as well that we are now grappling with. Of course, we all know about global warming. This is some of the data on CO2 and the historic data on CO2. And I would say we are in unprecedented and uncharted territory right now. We are reaching almost 420 parts per million. And the temperature rise since the pre-industrial level has been about, the global average temperature rise is about 1 degree. Now I put a marker of 2 degrees, and that is the agreement that we had in Paris. We still have that agreement worldwide. And the question is, why 2 degrees? That is an arbitrary number. But with 1 degree, we are now seeing the effects of climate change on the extremes of weather conditions that we are facing. And so we arbitrarily put a number saying that if you could only keep it below 2 degrees, it would be much better than 3 degrees, for example. So the question is, okay, so how long do we have? What does that really mean? So let me offer a quiz. Since I'm at a university, I offer quizzes. So here's the quiz for all of you. I'm going to throw some numbers at you, and I'd like you to think about what they mean, what are the units of the number, and what they really mean. And I'll give you the answer. There's no grading in this. The first number is 1. And this is 1 degree Celsius. This is the global average temperature rise since the beginning of the Industrial Revolution. And with the 1 degree, we're now seeing, as I said, some of the extremes of weather conditions that we are facing around the world. The second number is 2. This is the 2 degrees Celsius according to the Paris Agreement that the world came to agree on. The third number is 1,000. This is thankfully not 1,000 degrees Celsius. We're not talking about Venus. But if you are to keep the temperature below 2 degrees Celsius, we have headroom of a CO2 budget of 100 gigatons of CO2 with a 70%, roughly 70% probability of keeping it below 2 degrees. Okay, so this is 1,000 gigatons of CO2. Just to give you a reference, if you add up the weight of all human beings on this earth, the 7.5 billion human beings, that's less than 1 gigaton. This is 1,000 gigatons of CO2 that we have the headroom, because if you exceed the 1,000, we're going to likely exceed the 2 degrees as well. The fourth number is 40. And this is the 40 gigatons per year that we're emitting now, and that is increasing at roughly 1% per year. The last set of numbers is 20 to 30. This is the 20 to 30 years left for us to act on to address this issue, because after that, we have to keep the emissions to 0, which is going to be very, very difficult. Given the urgency and the magnitude and the scale of this problem, I think it is fair to say this is the defining dual challenge of the 21st century, providing access to affordable and secure energy for economic growth that we all need, but also simultaneously reducing greenhouse gas emissions. This is what we need to do, is to turn the ship around to provide the energy but reduce the greenhouse gas emissions. This is a very hard problem. Now, is there any good news in this? Are there some game changes that have happened? And indeed there are. So what are the game changes? I'm going to give you 3 of them. There are actually more than 3, but let me offer 3. The first one is unprecedented in history, is modern renewables at scale is the cheapest way to produce electricity. It is the cheapest way to produce electricity. In fact, it's become cheaper than natural gas in North America and electricity from coal in many other countries. This is unprecedented in history, but it is intermittent, and the grid is not quite designed for that. The second game changer is lithium-ion batteries. And this is transforming the electricity, the transportation sector. And it is likely that the cost reduction in lithium-ion batteries will be such that it will make electric vehicles range and cost competitive with gasoline cars before 2025, maybe 2023. And give it another 20 years and we'll see a major adoption of electric vehicles. This is transformational. It's once in a century event that is happening and is taking place. The third is the unconventional gas revolution, which has provided inexpensive and abundant gas, and that is replacing coal, especially in North America, and hopefully with some exports in other parts of the world as well. So this is the game changer. This is the good news. But you got to realize that this is a small fraction, at least the renewable is still a small fraction, but it's growing very fast. So if you put what is called the Sankey diagram from Lawrence Livermore Labs, and this is the supply and demand and how they're connected. This is only the United States, and there is a global one as well, but I'm just using that as an example. On the left-hand side, all these boxes are the different sources. These are, the total use of energy is about 100 quads of energy. And use the number 100, you can see solar is 1%, wind is about 3% or so. And the other use of energy, this is the supply side. In between, we have the infrastructure for delivery, for electricity, natural gas, oil, etc. And the right-hand side is the demand side of energy, where the energy goes in our homes, in our commercial buildings, in industry and transportation. And what we find that with all this growth that is taking place in renewables, which is really positive, if you do the accounting, we find that about 90% of the current budget in energy centers around heat, the conversion of heat, transmission, storage, and use. So given the challenges of addressing energy and climate simultaneously, and given the predominance of heat energy, it is hard to think of addressing the dual challenge without addressing heat. And so this talk is really to focus on that one, and we can come back to other subjects later on. So these are the 5 grand challenges, and these are picked with the highest opportunity for impact. We have not picked, for example, the conversion efficiency of combined cycle gas turbines or steam turbines, because there's a very nice paper out there by the panelists on this panel who have shown that it's not the Carnot efficiency that is the limit, but if you take the realistic efficiency, we are in these, at least conversion devices, we're almost at the limit. So the room for impact and the opportunity of impact is low. So these 5 topics have been chosen to make the maximum possible impact. So let me start with thermal energy storage. Given the renewables penetration onto the grid was never designed for fluctuating intermittent renewables. We're already seeing the effects of that today. This is the California electricity demand curve on a daily basis. And you find in the middle of the day that there's a big dip, which is often called the duck curve. About 14 gigawatts of solar and wind kick in, and the net demand is reduced, which is supplied mostly by natural gas. And when the sun sets, there's a huge ramp up of about 4 gigawatts per hour for 3 hours that has to be supplied by natural gas and other sources. And this is a diurnal, fluctuation that has to be supplied. Now this is at about 30 to 33% penetration of renewables on the grid and a gigawatt hour basis. But if you want to go to higher penetration, which we all want to do, and there's a goal to get to 60, 70, 80%, some of them people are saying 100% renewables. If that's the case, then the requirement for storage has to be much longer. So this is either 50 hours, 100 hours, or even seasonal storage for deeper penetration of renewables. And there's a wonderful paper out here in Joule that appeared this year on the need for storage. Now, if you get to longer duration storage, the cost for storage has to be such that it's very low. So what is that cost? And in this paper, I'm quoting this paper out here, it suggests that if you want to go for 50-hour storage, the capital cost of the storage has to be somewhere between $15 and $30 a kilowatt hour. And that is beyond the lithium-ion batteries today. Lithium-ion batteries are about $100 a kilowatt hour, and it's getting lower. But this is beyond that. And if you want to go to 100-hour storage, it has to be $3 to $10 a kilowatt hour, which means the bill of materials has to be lower than that. And if you plot that in terms of power cost and energy cost to provide these envelopes, it has to be within the envelope. And we see lithium-ion batteries over here, pumped hydro storage over here, compressed air storage, chemical storage over here, and we need to be here. This is the white space. So based on this, ARPA-E actually created a program on thermal storage, but storage in general, and thermal played a big role out here. And the idea is actually quite simple. Here you have electricity grid. You could use the electricity to either run a heat pump and store energy in a thermal storage medium. And by the way, that's what we do on Stanford campus. These tanks of water that you see are for thermal storage. So this is already being used. But you could potentially go to very high temperatures. And once you go to very high temperatures, you've got a lot of exergy. You could use it for direct heat utilization, or you could run it through an engine to actually provide the power to this. Now, one may think that if your power is generated from thermal sources, then you have a big Carnot penalty in both ways. That is true. But if you generate your power from solar and wind, you don't have the Carnot effect in the generation side. So even though the round trip efficiency of this may be 50 to 60%, the cost could be much lower. So there are two technical elements out here. One is the thermal storage medium, and the other is the heat exchanger, because that's cost. And so there was a very nice paper that was that appeared in Science on what is the white space in thermal storage. On the y-axis is the gravitational energy density and gravimetric energy density. On the x-axis is the volumetric energy density. And if you divide up storage, thermal storage into thermophysical storage and thermochemical storage, you see the two groupings, and there's a white space out here. And incidentally, lithium-ion battery energy density is somewhere over here. And we don't have a storage medium out here. And it turns out that this is very important. We need R&D to get there. The other part is the heat exchanger. And right now, and this is also unprecedented, we have things like 3D printing of heat exchangers where we can make shapes that we could not do before. And that could reduce the cost, reduce the overall volume, and thereby the cost of these 3D printed heat exchangers. So here's a huge opportunity. The question is this cost effective? So I'm going back to that same paper and the ARPA-E DAYS program, which I find it fascinating. This happened after I left ARPA-E. So, and so this is the new team out there that created. And this is the red line out here. This is cost on the y-axis in dollars per kilowatt hour. This is dollars per liter. And these straight lines out here are the energy, the volumetric energy density. And here is a straight line. If you want your storage, the overall cost to be about $10 to $20 a kilowatt hour, the medium cost has to be lower than that. So that's the red line out here. And so you can see the things over here, whereas things over here that don't fit into that. And also, as you can, along with the storage medium, is the container cost. So if you have high energy density, your container cost goes down. And so it is very important to be here. And we don't have anything out here. We have a few things over here. So the key technical challenges are high energy density, low cost storage medium, and high heat transfer rate. And these are all the projects, some of them in thermal storage, some of them in electrochemical storage, all being funded by ARPA-E. But this is just to highlight the thermal side of it. We cannot ignore that. And that ought to provide an option for thermal storage, for storage in general. long duration storage. A quick things about industrial processes. Cement manufacturing produces anywhere from 5 to 10% of the CO2 emissions. And there are two sources for it. Calcium carbonate, when you heat it, produces CO2, and that's pure stream of CO2 that comes out this way. And the energy that is used to raise the temperature to around 1400 degrees Celsius, that is either comes from a fossil fuel, either methane or coal. And that also produces CO2, but this is mixed with nitrogen because we use air as the oxidizer in this. And so that is mixed, and that requires carbon capture. There's a lot of work going on in trying to reduce the greenhouse gas emissions, because with a $40 or $50 a ton of CO2 price, this can be quite expensive for the cement industry. And so they need innovations. You could do, for example, electrical heating on this, or you could go hydrogen. I'll come to hydrogen in a minute. Hydrogen turns out to be very important. You could look at steel. And if you look at the blast furnace and the steel manufacturing, you have ore, you have coke and limestone, you feed it in, and you have many, many sources of CO2 and CO coming out. And we need CO2 capture and separation and capture. Now, there are some innovations that are going on in trying to eliminate the CO2 part. And the CO2 comes because you use carbon out here, and you use the thermodynamic driving force of carbon as a reducing agent to reduce iron oxide to pure iron, and thereby make steel. But the question is, are there other reducing agents? And sure enough, there are. One reducing agent is just electrons. And in an electrochemical system, this is an innovation coming from Don Sadoway's lab at MIT on using electrochemistry to go from iron oxide to iron. Or you could use hydrogen as a reducing agent and to make iron, but that has other issues of hydrogen embrittlement as well. Nevertheless, what we are finding is that hydrogen could be a very important element out here as part of our future energy system. But that hydrogen has to be greenhouse gas emissions free. It has to be at the gigaton scale, and this has to be less than $2 a kilogram, otherwise it's not going to make it. And it has to be at a scale, individual plants, that is relevant. That is 20 to about 200 tons per day of hydrogen plants. We can go to distributed scale as well, as long as it's cost effective, but you also have to have large scale plants. Now, hydrogen, a lot of people think is for transportation. Indeed, for long haul trucking, we'll see hydrogen use, but the use of hydrogen for industrial processes and for heating, I think it's a very important aspect. So how is hydrogen made today? Hydrogen is made from fossil fuel, either from methane, steam methane reforming, or coal gasification. And that hydrogen has CO2 associated with it. And if you add the cost of CO2 capture, you will get about roughly $2 a kilogram. So any other technique has to compete with that $2 a kilogram. And today we produce about 70 million tons per year of hydrogen, mostly for ammonia, for a fertilizer, and for petrochemical, for cracking, etc. So the question is, can one compete with this? Is the R&D going? And indeed there is. You could produce from water splitting, from carbon-free electricity at less than $30 a megawatt hour, maybe $15 a megawatt hour, and you could do electrolysis, which is the predominant R&D where it's going. And today it's at about $3 to $5 a kilogram, as opposed to $2, and the capex has to be reduced to make sure that this goes below $2 a kilogram, and that's where the R&D is going. But we should not forget that methane has a lot of hydrogen. So the methane part, today, ARPA-E has a program on thermocatalysis of methane, and this is still in the R&D stage. Hydrogen from methane has been used for a long time. This is for making carbon black. But to produce hydrogen and high-value graphitic carbon is still an R&D problem. And ARPA-E is now funded this, and we have a program in my lab on this as well. But this is a very important new direction that I think is worth exploring. Let me turn my attention to the third challenge, a low global warming potential. refrigerants. If you go back in history, we used to use CFC, this trichlorofluoromethane, as a refrigerant, and that was eating up our ozone layer in the atmosphere. So in 1987 came the Montreal Protocol, and it was ratified in the 1990s, early 1990s, to essentially eliminate CFC so as to protect our environment, our ozone layer. And this was the most successful global environmental treaty that we actually created. But the problem is that these refrigerants, HFCs, hydrofluorocarbons, have a global warming potential of greater than 2,000. And so now we have a problem with the leakage of these refrigerants. And it's been predicted that if you don't do much about the leakage of these refrigerants or find replacement for these refrigerants, the global warming from these refrigerants could be anywhere about 10 to 40% of the total global warming, including CO2, by 2050. So this is a big deal. So after the Paris Agreement in 2015, in 2016 was the Kigali Amendment to the Montreal Protocol to phase out HFC. But the challenge is that while there's a lot of R&D and other approaches like propane, et cetera, or CO2 as a refrigerant, we don't have a drop-in replacement. And it would be terrific to focus our R&D to find a drop-in replacement for HFCs to reduce, with a global warming potential, hopefully less than 1, which are non-flammable, non-toxic, and affordable. Because with the rise of refrigeration and cooling in emerging economies, this could be a major challenge. So this is an R&D area that we wanted to highlight. Moving forward, number 4, long distance heat transmission due with low exergy losses, with low losses. We don't have an equivalent of the grid for heat. We cannot do long distance transmission. And the question is, could we do that? Are there other sectors that have already shown that? Indeed, they have. We use small heat pipes. In fact, if you open up your laptop computer, there are heat pipes to move the heat from one place to the other at very low delta T's. And those heat pipes actually came from the space industry. And so now this is available, but the challenge is the following. These are typically less than a kilowatt in capacity. They operate around 100 degrees Celsius temperature range, and they have an effective thermal conductivity on the order of 10,000 watts per meter Kelvin, many times that of copper, and about 3 times that of diamond at its peak. The challenge is that we don't have that for large-scale heat transmission. So at tens of megawatts of power, 100 to 800 degrees Celsius, and with the same effective thermal conductivity. Imagine you had a plant like this, and you wanted to move the heat from here over there, and we cannot do that except for some steam use. We cannot do that for long distance transmission. So this requires R&D. Maybe the way to think about it, and here's a proposal for some dissociative chemical reaction of AB going to A plus V. This is an endothermic reaction, and the temperature could be controlled by the enthalpy and the entropy. And you could move these two streams, A and B, elsewhere, and maybe have a catalytic reaction to recombine them and have an exothermic reaction. And this becomes a moving enthalpy process of moving long distance, moving these fluids A and B. And this is, has been thought about not much, but there's and the chemists would know this, there's something called Diels-Alder chemistry, where you could do this associative and dissociative reactions, and that got a set of Nobel Prizes in the past. Or you could do it with metal oxide or calcium carbonate directly. But anyway, this is an area that requires thinking, because if you could do this, you could make these plants much more efficient. All these petrochemical plants were developed to reduce cost and make a product. They were not designed to reduce CO2. So if you want to use these to reduce CO2 emissions as well, you need other ways, and one of the ways to do so is to move heat, because 80% of the energy that are used in these plants is 80% is heat. And so managing heat long distance is very important. Finally, let me come to buildings. Buildings use a lot of our energy. In fact, 75% of the electricity used in the United States goes into buildings, and they contribute about 30 to 40% of the CO2 emissions. buildings are exchanging energy with the environment all the time. And these are, if you look at these infrared images, it tells you which part is hot, which part is cold. Wouldn't it be nice to have satellite imagery, high resolution satellite imagery, not in the visible range only, like Google provides, but in the thermal range with high spatial resolution, which we don't have today, and thermal street view. We have street view today, but we don't have thermal street view. And it would be terrific to have this and apply machine learning to identify the hotspots. In fact, in my lab, in collaboration with Ram Rajagopal, my colleague at Stanford, we have done this for the visible part of the spectrum. We have created an algorithm called Deep Solar to identify solar panels from visible part of the spectrum. And now we have the largest database of the GPS location and size of every solar panel in the United States. Now, we could do the same for the thermal side if only we could have the thermal imagery. But as you can see, these walls out here that we use in our buildings are passive. We try to reduce the thermal conductance, but sometimes we want to use the outside environment to bring that in. And sometimes we want to block it and reduce the conductance. So wouldn't it be nice to be able to control the thermal conductance? Because if you could do that, some studies have shown that we could save up to 10 to 40% of the greenhouse gas emissions. And can we couple it to thermal storage in ways like this? If you could only have thermal switches. We don't have thermal switches today, and there's a lot of research going into this and using thermal switches in a tunable way and leveraging storage to time shift and thereby use the environment to your benefit. But one of the things that I think Professor Jiang from Tsinghua University is going to talk about in heating and cooling in buildings, this is a building on the East Coast of the United States where it gets very hot and humid in the summer and very cold in the winter. And let me show you something that is striking. In July and August, which is very hot and humid in the East Coast, you have cooling that is expected, but you also have heating going on. And in the winter, in January and February, you expect heating, which we certainly have, but you also have cooling going on at the same time when you don't need it. So many of the buildings that we see around the world, it's fighting itself internally with heating and cooling simultaneously and dissipating energy. So it's very, very important. And I'm sure Jiang is going to take a view of this and look at a systems view of building heating and cooling, whether centralized or decentralized. And I'm really glad that he's on this panel in the future. So let me end with the following. We talked about the fact that 90% of the current budget centers around heat. So it's very important to address it. We have identified 5 of these challenges. Now, we can debate about this, and we scientists and engineers like to debate. That's good. That's very important. You can pick 1 or 2 of these. You can add a 6th one, a 7th one, if you think it's an important challenge, but you got to justify. But this is our proposal to you to start the dialogue. It's very important to start the dialogue and see what comes out, because it's not about the individual ideas, but the collective, where we are going with this. But let me also take this moment to take a shot at what is the new normal and lessons from history. As we all know, we are in unprecedented times. This is a moment in history that will have an effect not just in the next few years, but for decades and generations to come. And are there moments in history that we have faced this? And I'm reminded of my discussions with my colleague on Stanford campus, very distinguished gentleman, former Secretary of State George Shultz. And Secretary Shultz is going to be 100 years this year. He's 99 now. And he fought as a Marine. He's a Marine. He fought in the World War II, in the Pacific. And he has a perspective of history that is absolutely unique. So I was talking to him last week, and he keeps reminding us almost on a monthly basis, well, what were the lessons learned from World War II? And what were the mistakes people made after World War I? And one of the things people realized after World War II is that we're all in this together. This is one humanity. And it is it's a pretty crappy place after World War II. Millions have died. The economy is in shambles. And the question is, what is the future we want to define? And out of that thinking and leadership came things like thinking together, came things like the Marshall Plan, as well as the major global institutions that we have today, like the United Nations and others. So I think taking a lesson from that, lesson from history, and following George Shultz, let's define what the new normal ought to be. So here are some final thoughts for the discussion later on. Number one is that pre-COVID-19 had many sustainability challenges on multiple fronts. And COVID-19 has really forced us to take a step back and think about this. Number two is that the global economy today, just like in 1945, is in shambles. People are getting sick and some are dying. Many around the world don't have the luxury to think about the future like we are doing, but we do. We have the luxury doing so. And along with this luxury comes the responsibility to make the best use of this time. And this is the generational responsibility. We call the George Shultz generation the greatest generation the United States has produced. And it is really for our generation to think about what are we going to leave behind for our children and grandchildren. Number three, we, the humanity and planet this time, are all in this together. We need to think and act as a whole, not just in pieces at a time. Number four, we need to define what the world ought to be in post-COVID-19, the new normal. Everyone's talking about the new normal. What is that new normal? To address the defining dual challenge of the 21st century, there will be a post-COVID-19 world. Hopefully we will have the vaccines soon enough. But let's say it takes 12 to 18 to 24 months. What after that? What are the global institutions? What are the policy frameworks, the governance, the businesses to scale, to academia, and what is the R&D agenda that ought to be in the future to address this dual challenge of the 21st century? I hope we get some time to discuss, but I know this is a technical forum and we'll go back to the technical, but I just wanted to share with you that this is a moment in history that it is our generational responsibility and opportunity to think big. Now, let me stop here and I'll stop sharing and go into the panel.
Wonderful, wonderful. Thank you very much, Arun. Very inspiring and great vision at the end. I think a lot of people should be feeling the energy from that. We're now transitioning to the next phase of this session. I want to share a couple of things on my screen and ask our panelists to turn their videos back on, please. Get this going here. Screen share. Screen one. Okay, so we just finished Arun's talk. Now we're going to do the first of our several polls. So what I hope people are going to see in just about 10 seconds is a single poll pop up on your screen. Launch polling, here we go. Which of the 5 grand challenges that Professor Majumdar just showed us are you most interested in working on? And you can just click anywhere on there. I'll share the results shortly. I'll give you about 20 seconds to do that.
This is pretty cool.
It is. It's like a horse race. Coming around the outside, it's GW. No. Clicker's going up. We have about 50% response rate. Let's do another 10 seconds or so. I'll have a few more things to say about the protocol shortly. I see some people interacting with the Q&A and raising hand. Okay, so I think we're plateauing. I'm going to end the polling here and share the results. So I'm hoping people can see what's going on here. Among the 5, it looks like roughly equal 4-way split, but high energy density thermal storage came out in front with around 34%. Decarbonizing, long distance transmission, and variable conductance are similar, and the low GWP came in behind, although that may very much be influenced by the audience that's attracted to this session rather than any judgment of the overall significance there. Okay, so thank you. We'll have 2 more of these at the very end of the session. So I'm going to stop sharing those results. That was our intermission. So panel discussion is next, and let me show you again the protocol here. We're about to start the panel discussion. Now we're watching the time, and our panelists, including Professor Majumdar, have graciously agreed to stay up to an extra 30 minutes because we do anticipate lots of good questions and discussion. We'll assess that as we go. So just be assured that we're not going to rush everything in the next 8 minutes. And at the end, we'll have 2 other single question polls. For people who've joined us late, and as a reminder, your one and only communication pathway to us is the Q&A feature down at the bottom of your Zoom screen. It's not chat, it's the Q&A. And we have moderators looking over those and passing them on to me. Your questions are only viewable to yourself, but we encourage you, if you're comfortable, to share your name. If for some reason you want your question treated anonymous, that's fine too, but my default will be to read names when possible. And again, please be aware that this is all being recorded for eventual posting on YouTube, and we'll try also to disseminate the questions which were not able to be addressed today. Something for Professor Majumdar to think about. We've already seen plenty of people wondering about if the slides might be able to be posted, for example, as PDF perhaps down the line.
Sure.
Sure, he says, very good. Okay, so I'm going to use my platform as the moderator to pose the first question to our panelists. I'm going to stop the screen share and let them have a larger view of things on everyone's screen. And this is intended primarily for Akshay and Ravi. We've seen Professor Majumdar's perspective, and I'm just wondering if there's anything you might each want to add or perhaps reframe from this vision that Arun has shared with us.
So let me, can you hear me? I think 2 things I would like to add, right? One is to solve such a big problem, right? It will require academia, national labs, or other research institutions, as well as the industry to work hand in hand. Second is that we don't have much time. This is global warming and climate change is, as Arun pointed out in first few slides, that we have 20 to 30 years to solve this problem, right? So it's very, very important that the community, industry, academia, and labs work together hand in hand, and policymakers eventually. We have to influence the policymakers based on technological breakthroughs. So that I would say is more from the point of view of how the community has to work together. I just want to add a couple of more things to the technical things that Arun, topics that Arun covered. One on the air conditioning and refrigeration. There's another challenge, which is more of a hardware challenge, and maybe that's more exciting to this community, is today when we do the air conditioning, we not only use it for cooling, actually we use it also as a dehumidifier, right? And with growing demand of air conditioner, mostly in countries where humidity loss is pretty high, okay, like for example, India, it is very important to develop technologies which can very efficiently cool as well as dehumidify. So that's one thing that I wanted to point out, and which is really totally, it's one of the things that this community works on quite a bit. The second one, in the industrial sector, I would like to point out that even if we do electrochemical reduction of iron ore to steel, the high temperature electrolysis, the paper that Arun pointed out from MIT, that electrolysis happens at 1500 degrees Celsius. There are significant thermal management challenges at those devices, right? So again, that's another great opportunity for thermal community to really jump into some of these new processes. So there's a couple of things which just came to my mind when I was looking at Arun's slides.
Akshay.
Yeah, thanks. Very excited to see so many people here. Main thing I would want to, I guess, more so underscore from what Arun said. I think that my hope and my vision from this is that many people will feel compelled to get engaged on some of the problems we listed, and possibly others, as Arun mentioned. There could be others to append to this list. But the urgency cannot be overstated. We as a species are endangering ourselves with the infrastructure that we've erected to improve our quality of life. And at the end of the day, I think there are a few instances in history where scientists and engineers have come together and achieved something very remarkable in very short time frames. When we are mission directed, when we are coalesced around a particular focus, a particular direction, and particular mission. Examples such as the development of the atomic bomb, for example, and the way people have come together came together to get to the moon in a very short time frame. So large challenges where there can be a mission that's directed. My hope is that our community will take this as an opportunity to take a similar perspective about climate change and other sustainability issues. It's not just limited to climate change, but things that are very, very important for sustaining human life on this planet, and make that our mission so that we work on them collaboratively and with a great sense of urgency. There's just a huge need for more minds to be focused on these issues.
Okay, thank you. I've been looking at the Q&A, and we have 44 questions so far, of which we've answered mine. So we can see it's going to be a challenge to get through even a small fraction of them. Again, let me remind people that the raising hands mechanism is probably not how we're going to catch you. So please submit your questions to Q&A. And I just apologize, we're only going to get to some small percentage of the ones there, and you can blame me if your question's not getting raised. I think I would like to take the next one from Philip Iris, the editor of Joule, the journal, who's asking, what do you view as the near-term low-hanging fruit in terms of decarbonizing the industrial sector?
Well, first of all, sure, Ravi, go for it.
So I think there's a very nice report which came out from Columbia, right? Is the energy. So there are two aspects of carbon emission from industrial sector. One is the chemistry of the process itself. So for example, Arun talked about cement, calcium carbonate, you break the bond, you get CO2 out. Steel, you use coke or coal, basically, to reduce the iron to, steel. So that's the process related emission. And then you have energy emission, the emissions just related to how we supply the energy, which is primarily heat, okay? So changing the chemistry, there are a lot of other things. You have to figure out how it will change the microstructure of the new thing that comes out with with new cement or new steel and whatnot. But changing the energy input in the short term could be one of the things which I would prioritize, right? So can we convert the heating from, let's say, if we have a very cheap renewable energy available, can we just do simple brute force Joule heating, right? That's one. Or if we have biomass or I would even say renewable hydrogen, green or blue hydrogen, right? Then maybe switching the natural gas, which is used in most of the industry today, or oil, to that blue or green hydrogen, right? This, at least from my perspective, that is in the short term is more doable than changing the fundamental chemistry of the system itself.
Yeah, I would agree with that. I think there are pure streams of CO2 that you could use today. There's a policy, at least in the United States, called 45Q that actually pays you to do that and take the CO2 away. And I think I can't overemphasize carbon capture and doing something with the carbon capture, utilization, sequestration. But the carbon, we have to do that because it's going to be very hard to switch to something totally new in a matter of few years. So those two, I think, are some obvious ones. There are, I think, in the industrial processes, the thermal management side, there's a lot of waste heat that goes out that is not being utilized. Even managing the heat as opposed to converting it to something, managing that heat and utilizing the heat properly could go a long way.
Yeah, I just want to add one thing. I think it's an interesting question. I totally agree with Ravi. I think essentially the industrial problem is broken into two parts. There's supplying the heat, and then there's the actual CO2 emissions associated with the reactions themselves. the reactions themselves are probably a much harder problem, more longer term problem, because for the most part, you probably have to reinvent the infrastructure at the very least, or do a different reaction or do something very, very different. Possibly switching to using low cost renewable energy as a heat source is interesting. I think it's probably something that could be implemented in the shorter term. I agree with everyone else in that respect. But I think there's some interesting technical challenges that go with that, right? Because a lot of the heat that we're looking at, if you talk about steel or cement, you're talking about 1,1500 degrees C. And there aren't a lot of options for what heating element to even use, right? Because these things occur in air, right? So a lot of metals start to oxidize a lot. You get them that hot in air. So you start thinking about other heating elements or alternative materials like silicon carbide, which again is going to rely on some kind of oxide scale like silica in order to survive. And so it'll be interesting to think about not only what other materials or what ways you can do the heating, but also somehow I think what would make it happen quicker is to find some way to take advantage of the fact that it's electrical in nature, in the sense that you have effectively pure exergy rather than sensible heat that you're putting in. So you can put in all of your heat at the peak temperature. To the extent that you can take advantage of that and somehow lower the cost of the overall process, then you can actually make it cost effective to implement a new heating scheme, which now has the benefit of lowering the CO2 emissions, but also could possibly improve the process overall. So I think those are the kind of opportunities we want to look for. Those may have quicker implementation because they have some immediate cost advantage. Aluminum is another one I would throw out. That's a huge amount of waste heat. The waste heat there is largely related to the way the process is done. They have a particular interface in there with a salt that is protecting the salt that's actually facilitating the reaction. And so you end up throwing away a ton of heat because they're trying to keep a frozen ledge inside the smelting pot. And so thinking about clever ways to actually reduce the heat leakage or reuse the heat to offset the electricity that goes in. These are the types of things that are, seemingly straightforward in concept. The real key is, can you come up with a real practical solution that can be implemented? Because these are industries that are very risk averse, right? I mean, they have a product, they make a lot of money selling it already, and you want to change that. And so you've got to have something very robust that's not going to fail, that's not going to threaten their economic viability going forward.
I just want to add one more thing, which I think has not been, at least in my opinion, has not gotten significant attention. Provide localized heating. Okay, so there's many ways to. One is that one of the reasons we waste a lot of heat is because we are trying to heat a lot of other areas of whatever we're trying to make, right? And actually, what heat is really needed at some point, right? So localized heating is another area which I think is very exciting from science and technology point of view, and that can also solve a lot of the heat leakage issues and overall increase the efficiency of the plant.
Okay, I'm going to keep it going. There's so many good questions here. A very timely and sobering one from Shigeu Maruyama as well as Dino Megarides. In this moment of COVID-19, we've seen that in the near term, CO2 emissions have been greatly reduced. So that kind of brings to mind, one, do people know factually how much the reduction has been? And of course, bigger picture, where's that pointing us in the future if we were to shift more towards telework, less conference travel, that type of thing?
Yeah, I mean, first of all, let's also, the panelists, take an opportunity to thank Chris for managing this whole panel. We really appreciate you taking the time to do that, and your expertise on managing Zoom has been noted. So and we have to learn from you how to manage things. But going back to yes, I mean, it is indeed true that we have gone down about 5.5 to 6% emissions reduction. Obviously, as we are now seeing a turmoil in the oil industry, the whole oil economy, but trucking has actually gone up because we still need the stuff. So I think, look, this is a massive global experiment that is being run that was not planned. And I think we need to really look at this very carefully as to, in planning, where we need to go in the future. Where are the emissions coming from? There may be fugitive emissions that we are not aware of. That how come with all this economic downturn, we're only going down 5.5 or 6%? Because we need to do 6-7% per year for the next few decades. So I think this is an opportunity. Obviously, we should have gone down more in terms of emissions. We're not. So, but let's use this opportunity to learn what the heck is going on and why are the emissions only going down 5.5% in this global massive experiment. I don't know the answer to that, frankly, but I'd love to learn.
Okay, so I'm keeping an eye on the time. We're around 10 minutes past the nominal ending time. Let's go for another 20 minutes or so, and I think there'll still be plenty of questions after that. We'll try to post online, but let's plan on another 20 minutes and 3 minutes of wrap up, ballpark. Next, I'd like to take a question from Riley Hanus of Georgia Tech. In regions with significant wind or solar, it's well known that the price of electricity sometimes goes even negative. So what is that telling us? Is that going to impact the long-term adoption of these technologies? Are there other technologies that could leverage this deep change that's happening?
So let me answer this question. I think this is a question which I would say has many different implications, okay? And absolutely, this question is right. Even in California, there have been a couple of days in the past where the price of electricity has gone negative because we were generating more energy from solar farms during the day, and then that the state really needed, right? But again, what Arun shared, one of the first challenges is coming with the cost-effective storage, right? So if you really have a cost-effective storage, that's going to change the game a lot, right? I mean, it's going to be a big impact. That's one. Second, I would also say there's a lot of discussion going on that since you have such cheap electrons available, you can use those cheap electrons to create new chemicals. Let's take hydrogen as an example. One of the biggest reasons there's significant interest in hydrogen is because the expectation is the cost of energy is going to be a small fraction now to create renewable hydrogen. Okay, it's going to be the capital cost of electrolysis and stuff, right? So that basically tells you that we may see a change even in the way we use different industrial processes, okay, to create things. And if we can have, because the energy cost is going to be a very, very small fraction, but it changes the problem in some other directions. That means you also have to figure out technologies which only works 25% of the time because energy is only available from sun 25% of the time. So we will expect, at least my suspicion is that we will expect many different strategies in the future, and it's not very clear which is going to be it's not going to be one solution fits all. That's what I feel. I would love to hear from our other panelists.
Asi?
Yeah, just to underscore Ravi's point. I mean, I think the fluctuations in going negative is related to storage. I mean, it really highlights this point that an electron is only valuable if you can get it when you want it. That's the way our grid is set up, and so giving us electrons when we don't necessarily want it or don't have a use for it has less value. And so, but I think that the problem is even broader than just figuring out how to store electrons. I think there was another one of the grand challenges Arun pointed out, which is the idea of possibly storing the energy in, for example, maybe the walls of a building as heat as its intended end use is going to be. So with buildings being such a large fraction of energy used in the first place, maybe you don't have to have electricity storage. Maybe you can have heat storage because the final use is going to be heat anyway. So there are other modalities of how you can think about storage. I don't think we need to just be restricted to electricity storage, but I do think electricity storage is a very straightforward one that would definitely have huge applicability.
Okay, almost overwhelming number of questions here. Here's an anonymous attendee question. How much in the big picture could we rely on electric cars to reduce the greenhouse gases once you take into account the full life cycle CO2 and the battery manufacturing considerations as well? Is it really that much of a win once that's all taken into account, cradle to grave?
Yeah, if you're generating electricity from coal and then using it in your car, there's not much benefit. In fact, you could have probably more emissions that way. I mean, we are kind of looking at the future where it is easier to decarbonize the grid. Not that it's easy, but it's easier to decarbonize the electricity sector and the grid than many other sectors. And the question is, can the transportation sector leverage that opportunity and go and reduce their emissions. And I think we're looking at the future, not today, but looking at the future where we have deep penetration of renewables. And then, of course, life cycle cost of transportation goes down with electric vehicles, including the life cycle of the battery. Having said that, I think the recycling of the battery is a very important issue. The using green electrons to make the battery in the first place, and secondly, recycling of that in a environmentally friendly, sustainable way is critical. And I think that needs R&D. I'm not sure enough R&D is actually going into the latter part of it, although some of that has started.
So I just want to add a couple of other things. It's not, let's say, for United States, that's an example I can give. So now, even if with natural gas, as we know, natural gas power plant, the combined cycle goes, let's go back to thermodynamics, right? Natural gas combined cycle power plant efficiency right now is approaching 55 to 60%, okay, right? And in fact, in the United States, natural gas is a bigger proportion of energy than coal is. And then we get a lot of energy from hydro and nuclear, right? So if I do that math, the mix right now roughly is primary to, site to primary energy ratio is 2. So, you know, you're burning or something is 2 times what you need in the form of electricity, right? So I think the economics has changed, that energy economics, I don't mean some sort of dollars, right? Has changed now in favor of electric vehicles because you have less and less coal on the grid. And even though natural gas is fossil energy based, still it's much, much more efficient conversion process than it is with coal, right? But for the rest of the world, I have not paid attention for some other parts of the world, how this mix from primary to secondary energy is changing. But there is a critical point where you will see that you are better than burning gasoline.
Okay, next a question from Mark Johnson, and this is about low-grade waste heat. A large amount of waste heat is actually below around 230 Celsius. And so what really is the roadblock to efficient utilization of this heat? Is it more about thermal management, the heat sink, the conductance of the heat sink rather than the source temperature? Any technical comments about that?
I mean, I can, I don't even want to go ahead, or I can.
Asi has thought about this a lot. Asi, you want to?
I'll let you guys go. I mean, I think my answer might get kind of long.
Yeah, I mean, the one thing I would say is that low-grade waste heat, trying to utilize that is, you know, when we were in ARPA-E, we kind of had a thumb rule. If you got low-grade waste heat, keep it as heat.
Yeah.
Don't try to convert that.
Right.
If you've got high-grade waste heat, then there's a lot of exergy. So if you've got low-grade waste heat, keep it as heat. And the question is, can you utilize it another way, which is what we do in cogen and things like that. You know, people think that we can get to really small delta T's and thereby, reduce the waste energy. The lower the delta T you go, the larger the heat exchanger you need. So your cost goes up. So there's an optimal delta T that you need to be able to minimize the cost. And trying to go below that is frankly not helpful. Ravi?
Yeah, I just want to echo the same thing, right? I mean, let's go back to thermodynamics. This is a thermal forum. Let's just go back to basic thermodynamics, right? If you have low-grade waste heat, the Carnot efficiency, the best one, itself is so low that you put 100 watts in and you will get 99 watts again output as a heat. The heat efficiency is so low, okay? So it goes back to basic thermodynamics, second law, okay? So I think, as Arun pointed out, we have, at least I know the numbers in America, and I'm sure it's very similar numbers in Europe and other places. In the United States today, at the building level, roughly at the site level, we use roughly 9 quarts of electricity and 9 quarts of heat, okay, roughly. Okay, number has changed a little bit here and there, but roughly same, equal. So I would say that use heat as heat. I mean, you at the site level, your requirement for just providing comfort in forms of thermal energy, that requirement is same as providing electricity for lighting and running your computers and stuff, right? So let's not try to convert it, right? And I think, but having said that, it goes back to the fourth challenge that Arun pointed out. If you don't have long distance transmission, okay, then then you cannot really utilize it, right? And I think that's the biggest advantage of converting electricity. You can do long distance transmission, right? So there is the technological challenge. If somebody figures out a long distance transmission, I would say that we will see significant innovation in utilization of low grade heat.
Yeah, I was just gonna let me just add that even when you try to do using the low grade heat as heat, this point Arun brought out, I just want to underscore that, which is there was something he used to say, Arun, energy is dirt cheap, so we treat it like dirt. It's at some point we have to also think about the value of the heat, and if the value of the heat is so low, then you cannot even afford a device to convert it or move it anywhere, or to even exchange it and put it somewhere else. And so this necessitates either extremely cheap heat exchangers or means of moving heat from one medium to the other. But I think as a community, it's useful for us to begin to think in terms of levelized costs of heat rather than just levelized costs of electricity. Like, what is the actual value of the heat as compared to the equipment you're going to use to move it around?
Okay, we're only going to have time for 2 or 3 more questions. Alejandro Datas asked, he would like to know your opinions on challenges for thermal insulation, especially in the high temperature applications, aerogels or other types of things, or more lower cost ones. So let's hear about high temperature insulation, please.
I'll comment first. I think that's a huge one. I think as we start to talk about decarbonizing industry, we start talking about other applications where we're dealing with heat at very high temperatures that's got very high exergy. The issue is, how do you keep it? How do you keep it and keep it cheaply? There are a small handful of options when it comes to trying to insulate. There are some step changes that happen around above about 1,000 degrees C, where it's difficult to use things like silica, above about 1,500 degrees C, where it's difficult to use things beyond that, made out of alumina and zirconia. And when you go really high temperatures, 2,000 C, where some of the things my group looks at, there's only one option, which is carbon. We would love to have, for example, like a porous tungsten, right? At those high temperatures, extreme temperatures, it's radiatively dominated. And so we're essentially relying on the optical properties of carbon, which are very high emissivity, right? I mean, it's really the conduction portion is small compared to the radiative portion. So you could actually use porous metal and actually should be a better insulator than carbon. So I think there's some interesting things. There's some interesting regimes and places to play. Keeping things cheap is critical. That's absolutely critical. I mean, we can always make things that might outperform. I'm sure someone may be able to make some kind of porous tungsten, but the question is, can you make it in an economical way that we can actually use it? So I think there's a huge value for technologies in that nature. There's also something we often talk about, right, is that the spectrum of thermal conductivity is very, very different than the spectrum of electrical conductivity, right? So we don't really have what is the equivalent of perfect thermal insulation, right? We always have some thermal leakage that is substantial. If we had thermal insulation or something with a thermal conductivity, some solid that actually could hold its own weight with a thermal conductivity 4 and 5 orders of magnitude below that of air, then we now get to the place where I think we have something like a true thermal insulator, and we can insulate a wire and not worry about any leakage that's coming out. But we don't have that. So I think the insulation still plays a very important role. It's a significant part of the cost because we need so much of it, because the length scale's got to be large because the thermal conductivities are not low enough. And so from where I stand on a theoretical standpoint, there's no real intrinsic lower bound on thermal conductivity or upper bound. There's nothing physical that prevents you, that says you cannot have a thermal conductivity 2 or 3 orders of magnitude much lower than air. We just haven't found it. We haven't figured out how to do it yet.
I just want to add one thing, that it is a very, very good, it's a big open question. I'm glad somebody asked this question. Another thing I will also always remind that high temperature brings a lot of other challenges. Reliability is very, very important. Your oxidation and all these sublimation, oxidation, all these issues become very, very important at high temperatures, right? So that is something I think, I'm assuming a lot of graduate students and postdocs are also attending this. If you are taking up this challenge, always keep in mind that look for things, other things just beyond looking at time zero measurement of a performance. because that's reliability is as important as just getting a really good performance in the beginning.
Okay, I have a couple last questions in mind, and again, I'm just so sorry. There's so many good questions and not enough time. There's a slight curveball, different perspective from an anonymous attendee. What is your advice for students? How should we think about making an impact in this issue, especially if we may not have a background in the engineering topics discussed today? Are there alternatives, perhaps, to academia and R&D? So I think you could answer it for the technical people and also for the non-technical, perhaps.
I would love to hear from Arun with his vast experience.
Well, first of all, if the student is a graduate student, the job of a graduate student is to graduate. That's number one. So, look, I mean, the field of energy is broad enough to offer an umbrella for any walk of life to participate. If you have a technical background, that's great. That helps you kind of understand some of the nuances on the technical issues and actually helps you to look at the policy side as well, and the business side and the finance side. There's so many aspects of it. The social equity issues are so important in energy. Who gets the benefit of a tax credit or something else? And so my suggestion to the student would be, do what you're doing. Graduate from whatever you field you're in, get the depth of understanding of that particular field, but also keep your eyes and ears and education wide open for beyond your discipline, because you really need to understand the other aspects of energy and climate, frankly. And it's very important to have this holistic panoramic view if you are to make the right decisions, and if you are to suggest people to make the right decision as well. So the broad-based education, you almost need to be a T or a pie. You need the depth of understanding in a particular field, but you also need to know the breadth. And that, I think, is the biggest value given the magnitude and the urgency of this issue.
I'll add one comment on that. I think that we on this panel have our own contacts and communication with the various fields that we intersect with, but to the extent that there's a problem that sounds interesting here that has not been really discussed in the field that you come from, I think that it'd be really valuable to help communicate the urgency of these challenges to other communities. So even in just translating this message and getting the word out could be a huge impact. And also I would say, I personally think a lot of the coolest ideas are going to come from these collaborations in other fields. I don't think it will just be us solely. I think it will be us learning new disciplines and getting exposure to new disciplines from folks from other disciplines that are experts there. And they'll point out things that we missed that we may not have known about. And I think those interdisciplinary, multidisciplinary approaches are where some of the biggest advances will come from.
Okay. So with 5 minutes left, at the organizer's request, there's a distinguished colleague on the attendees, Professor S.K. Das from IIT Ropar, the director of IIT Ropar. So Gong asked me to unmute this attendee and let him speak a question rather than it coming through the moderated Q&A. So I'm going to unmute Professor Das and let him pose his question, and I'm going to transfer over and share my slides for the last little phase here. So Professor Das, if you're capable, I believe I've allowed you the permissions to talk, so please go ahead with your question for the panel.
I think he's muted. Sarita, I think you're muted.
I don't see him as an attendee here.
Can you unmute him?
Here he is. I'm allowed to talk. Let me do it again. I saw him for a second. So I'm sorry to say, Professor Das, I believe I'm clicking on the privileges for you and then your name disappears, but we're not able to hear you. So let's give it another 15 seconds. Maybe while he's working on that, if possible, I'm going to show you the last slide here. Screen one. Okay, so in the wrap-up phase, first, I urge you to really think about the presentation next week, same time, same Zoom coordinates. Professor Rongui Yang from the Huazhong University of Science and Technology will be sharing some of his recent work on radiative cooling using the atmospheric window to exploit the cold temperature of the universe in deep space. And I saw several questions in the Q&A related to that. It's both a great scientific fundamental topic as well as very practical, and you'll see some outstanding, I think, scalable manufacturing technologies as well. So we really urge you to continue participating and attending that next week. And then here's the last slide. And I'm sorry for Professor Das if the technology is just not working for us right now. In about a minute, I'm going to put up the last 2 poll questions. How frequent should these events be, and what's your own background? Are you coming from academia or industry or so on? In addition, the organizers are extremely interested in your feedback as an event. So feedback you'd like to give that doesn't lend itself to the poll, please type that in the Q&A. That's our feedback channel. Every single comment in the Q&A will be read afterwards by the organizers. Things about the technology, suggested topics, anything that can help make this a better experience all the way around, please do that. And also, you are highly encouraged to advertise this event more broadly to your networks. This is our very first one, an outstanding turnout of more than 800 people we've seen on the line here. And you're also highly encouraged to sign up on the email list linked through this InnoTherm MIT EDU website, because right now everything's being disseminated on an ad hoc basis through everyone's networks. But to make sure people don't miss anything in the future, you're highly recommended to do that as well. Okay, so I see my colleagues in the back room, so to speak, are also unable to get Professor Das here. So I'm very sorry about that, Professor Das from IIT Ropar, the director, unfortunately. But I think we'll just have to move on at this final point. We're coming up on our targeted ending time. Let's also remember to thank the people that helped make this event happen. We've already heard about Evelyn Wong and John Lienhardt, the departmental leadership at MIT on the thermal sciences side, and lots of students and staff. I only know some of them, KK Shu, Simo Pajovich, James Zhang. I know there's others as well who have to get this all set up, all the preparations and managing questions as well. So I'm going to show you the 2 poll questions, and then we'll leave the Zoom line open for another 5 minutes for you to continue typing comments in the Q&A. Here comes the first poll. Poll question number 2, launch polling. How often should we do this? Weekly, bi-weekly, or monthly? Give you 15 seconds on that. Weekly, bi-weekly, or monthly? Okay, I see things converging there, so I'm going to end that polling. Share results. I think you can see that bi-weekly or maybe weekly looks about right. And let me go to the last poll here. Stop share results. Where is our final poll? Launch polling. What's your background? Faculty, industry, government, students, postdocs, or other? We'll let that go for 15 seconds or so.
Faculty and students are competing.
Oh yes, come on faculty, step it up faculty, you're running slightly behind. We can all see it, you guys can't see the horse race. Okay, I'm gonna end polling with 80% turnout, share the results. Students and faculty with a good dose of other sectors as well, including the other. Okay, so that's the end of the polling. So I think this is now gonna be the end of the formal session. The line will stay open for 5 minutes. Again, for any feedback, please do type it in the Q&A, and the organizers will surely review it and value that as well. Okay, so with that, let's close here. I'm Chris Dames. It's really been a pleasure hosting everyone here today in this inaugural session of the International Colloquia on Thermal Innovations. We've had people everywhere around the world. The sun never sets on thermal issues in the energy sector. So whether it's good morning, good evening, good night, or good day, I hope you've enjoyed it. I hope everyone is safe and doing well, and we hope you'll be participating in this in the future. Thank you, everyone. Bye-bye.